Next, we'll look at example 40. In this experiment, we're going to roll two distinguishable fair dice and record the up faces. We'll then define a random variable x to be the sum of the two up faces. And so this is a distribution that we have, it's an experiment that we've seen before and a random variable that we've seen before. We calculated the PMF and the CDF of this random variable in a previous example. In fact, here is the PMF for that random variable. And see here is the CDF. So in this example, we're going to calculate the expected value of x, the variance and the standard deviation of x, and also the skewness and the kurtosis of the distribution of x. And so to calculate the mean of the distribution of x, we'll use the definition formula. And the expected value of x, the mean of the distribution of x, is the weighted average of the values taken on by the random variable, the weights being the values of the PMF. And so I'm not going to type in or show here on the slide all those products, but it's easy to show, it's easy to calculate that that weighted average, the expectation, is 7. So the mean of this distribution is 7. The variance, I will also use the definition formula. In other words, the expected value of the square of the differences between x, the random variable x, and its mean. And when you do that calculation, you get 35 over 6, which to 4 decimal places is equal to 5.8333. For the skewness coefficient, we'll first need the third central moment. All right, and I'm going to use this formula here to calculate those values, or that value. And so we need to plug in the value 7 for the mean, which we've done here. And when we go through that calculation, we get a value of 7. I'm sorry, value of 0. And so then the skewness coefficient turns out to be 0. And so that implies that the distribution is symmetric about its mean, which if you go back and look in the notes at the PMF, the graph of the PMF, you'll see that it is in fact symmetric about 7. And then finally, the fourth central moment, right, again, using the definition formula, and we end up getting 80.5 for the fourth central moment. And so the kurtosis is the fourth central moment divided by the square of the variance, all right, and that turns out to be 414 over 175, or 2.3657, rounded to 4 decimal places. Now, to show some of these calculations on the TI-84 calculator, I have entered the sample space and the values taken on by the PMF in the first two lists. And so then, to do these calculations, we'll first calculate the mean. We know that that's going to be the sum of the inner product of list 1 and 2. In other words, the sum of the products of the values of corresponding entries in list 1 and list 2. And so that turns out to be 7. Then to calculate the variance using the definition formula, we calculate the sum. All right, we have list 1 minus the mean, quantity squared, times the values of the PMF, corresponding values of the PMF, which are list 2. And so we get 5.83333 and so forth. I can convert that to a fraction if we want to see the fraction. So 35 over 6. To calculate the third central moment, I'll just grab that expression there and edit the expression. So I'll get 0. Because the variance is positive, I know that the skewness coefficient is well defined. 0 over this quantity raised to the 3/2 power, which is just going to be 0, so there's no point in doing that on a calculator. And then we'll next calculate the fourth central moment. Okay, 80.5. If you want that as a fraction, you can get it that way. Okay, and then the kurtosis is equal to the fourth central moment divided by the square of the variance. Okay, and so let's see here, yeah, 414 of this, so 2.3657 rounded 4 decimal places. So you see how easy that is to do on the TI-84 calculator. It's quite a bit more tedious to do by hand, but if you've got a random variable that has a lot of values in its sample space, then it gets even more cumbersome to do. Now let me also show you how to do the calculations in the spreadsheet. And so I used the same spreadsheet template that I used for the previous example. All I did was I just expanded the number of rows here in this section of the spreadsheet. So retaining all of those formulas, everything is built in here. So once I've got it built, once I have that template built, then I don't have to change any of the formulas down here. All I have to do is include rows here in the body of the table, and that will ensure that the formulas are retained in these columns as well. So I've got the values of the sample space here in this first column, the integers 2 through 12. I've entered the values of the PMF in the second column. And once I populate those values, these quantities are automatically calculated, as are these. And so I get everything is done very simply in the context of this spreadsheet. So we see here that the mean is 7. The variance is 5.8333. The skewness coefficient is 0, and the kurtosis is 2.3657, which are the same exact values that we got when we did it by hand, and also using the TI-84 calculator. Okay, so that's it for, well, I guess we've got one more slide here for this example. So just wrapping things up, to summarize, the mean of the distribution is 7. The variance is 5.8333. The third central moment is 0. The fourth central moment is 80.5. From these last three quantities, we get the skewness and kurtosis, the skewness being 0, which again tells us quantitatively that the distribution is symmetric about its mean. So if we had not looked at the graph of the PMF, we would be able to tell immediately that it is symmetric about its mean. And then the kurtosis for this distribution is 2.3657. All right, and in and of itself, that's kind of meaningless. But what we'll typically do is use the kurtosis by comparing the kurtosis of one distribution with that of another. All right, let's continue on looking at the next example, example 41. So roll a fair die and a weighted die and record the up faces. The weighted die is constructed such that the probability that the die lands with a given face upwards is proportional to the number of pips on that face. Let the random variable x be the sum of the two up faces. Then we want to compute the following: the expected value of x, the variance and standard deviation of x, the skewness and the kurtosis of the distribution of x. Now, here is the slide that we looked at in a previous example when we were dealing with this particular experiment of tossing a fair die and a weighted die, and then letting x be the sum of the two up faces. All right, and so here is the PMF for this distribution. Okay, and so we'll be using this to calculate the mean, the variance, the skewness, and the kurtosis. Here is a graph of the PMF, and so you can see that the graph again is not symmetric. It is skewed. All right, and you tell me which direction does it look skewed? Okay, we'll investigate that when we calculate the skewness coefficient. So calculating the mean, we'll use the definition formula, and if you go through that process, you'll get a value of 47 over 6, which is 7.8333, rounded to 4 decimal places. So the mean is just a little bit higher in this situation than it is when the two dice are fair. The variance of this distribution is 5.1389. The third central moment is not 0 in this case. Okay, that right there would tell us that the distribution is not symmetric. All right, but we're going to calculate the skewness coefficient to get rid of the units in this measure. So the third central moment is negative 1.9259. To get the skewness coefficient, we divide that by the variance raised to the 3/2 power. And so when we do that, we get a skewness coefficient of negative 0.1653. And so that tells us qualitatively that the distribution is not symmetric about its mean, and in particular that it has left skewness, negative skewness or left skewness. Okay, and then the fourth central moment turns out to be 65.0255. We divide that by the square of the variance to get the kurtosis, and so the kurtosis for this distribution is 2.4623. Now let me bring up the results obtained from the spreadsheet. Again, I'm just using the same template. In fact, I didn't. If I use the same spreadsheet that I used in the previous example, I don't have to add or delete any rows. All I've got to do is change the values in a single column, this one right here. And everything else is calculated automatically. And so the mean, the variance, the skewness, and the kurtosis are calculated automatically. So from the spreadsheet, the mean is 7.8333. The variance is 5.1389. The skewness coefficient is negative 0.1653. And the kurtosis is 2.4623, which are the same values obtained by hand. All right, and so going back to the slides, all right, and to wrap things up, okay, here are the values we calculated. So we've seen three examples of discrete random variables where we find various characteristics of the distributions of those random variables, the mean, the variance, the skewness coefficient, and the kurtosis. We can do those calculations by hand. We can do the calculations with a spreadsheet. We do the calculations on a calculator like the TI-84 that has list capability. You could write a program in some language to calculate these things as well. So I would strongly encourage you to create, for example, one of these spreadsheets, a template spreadsheet that you can use for calculating the various moments and the various characteristics of the distribution. That's going to come in very, very handy in some of these labs. So again, I would encourage you to create something like that.